Okay, welcome back. This is 6.4, and we're going to be talking about thermochemistry. And if you'll notice down here below thermochemistry, I don't have any chapters or page numbers. That's because we're really getting into the AP part of pre-AP, a lot of extension and a lot of stuff that's probably not going to be in the regular chemistry textbook. So I don't have any reference to pages down below there. All right, so in thermochemistry, fuels like natural gases, propane, butane, wood, coal, gasoline, and diesel historically have provided society with energy, and most of this stored potential energy can be released through the combustion reactions of these products. And while the absolute potential energy is not important because there's no way that when we burn these, we can get 100% of the energy out. Some of that energy is lost into the environment. The change in the potential energy is important. And we can use that change in potential energy to run machinery, cook food, heat our homes. And we've been doing this for millions and millions of years since, caveman first discovered fire. Well, we're going to be using a symbol, a triangle and an H, and this is used like right here to represent the change in heat because most energy is released through combustion and or exchange of electrons. So this delta right here, we're going to refer to as the change in. So anytime in science when you see a delta, that means the change in something. Like delta T, we saw as a change in temperature. Okay, so there's specific types of enthalpy or heat exchange we're going to be talking about. You'll see delta H fusion coming up in our next section. You'll see delta H VAP, that's short for vaporization. You may see a delta H solution, a delta H reaction, and a delta H combustion. So there's going to be a lot of delta H's that you're going to see. We're going to see one in this section where it's delta HF, and that's the heat of formation. So there's a lot that you're going to be seeing here. And again, these just mean the change in heat or the change in enthalpy. Okay. This is one thing that you really, really need to remember. Okay, that's key. Breaking bonds requires energy input, while bond forming results in energy release. So we have these reactions where we're breaking bonds, and we have reactions where bonds are reformed, and it's an input of energy in one and an output of energy on another. So broadly speaking, we have two different kinds of heat exchange. There's called endothermic and exothermic. So endothermic requires a net input of energy, and the energy of the products will be higher than the energy of reactants. Now you see a dotted line here. That's because what happens in between this is sometimes complicated. For example, we can start with our reactants here, and then for some reactions, it goes up like this, and then it ends. So this is the energy that's required to start the reaction. Once the reaction starts and then finishes, the energy is here. Sometimes we'll have reactions that start, and then they'll have several humps like this, and then it finally ends out. And this kind of stuff like this, we'll talk about in AP chemistry, and we'll get deeper and deeper into that. You may see some of these graphs like this because this is typical when we start talking about endo and exothermic reactions. But basically, overall, you have your reactants that start with this amount of potential energy, and they'll end with this amount. Okay, and this is called endothermic. So it actually stored energy within these bonds. The products of that reaction have more energy than the reactants. Okay, endothermic. And the delta H for this is always going to be greater than 0. So it's going to be a positive energy. On the other hand, there's another reaction called exothermic, and this is when they release energy, and that's when the products of a reaction have less energy than the reactants. So the reactants start at this much energy, and then as the reaction progresses, it releases a lot of energy, and the products end up with less energy. So our delta H, or our change in enthalpy, is going to be less than 0, so you'll always have a negative number for an exothermic reaction. Okay, so remember, a positive number indicates an endothermic reaction, and a negative number, the loss of heat to the surroundings, is a negative number. Okay, now when this amount of energy, when a numerical value is placed on that and included in the reaction, this is called a thermochemical reaction. So here on the endothermic reaction, we can see that we have 572 kilojoules per mole of reaction included in this. So it's plus H2O, and that's going to yield 2 moles of hydrogen gas and a mole of oxygen gas. So we see here that the energy value is incorporated as part of the reaction. When it's on the reactant side like this is endothermic. It takes heat to put into the reaction to get the products. And on the other hand, the exothermic reaction, we have our reactants here on this side. Okay, and then heat here is a product. So this is releasing heat as a product of the reaction. So that heat will be on this side. Now remember, in chemical reactions, we don't have, just like when we talked in our redox reactions, we don't have, this minus this. We don't have A minus B. It's always plus signs that we use. Okay, so that is why here we have the energy as a reactant, and here the energy is a product. Okay, and that's endothermic and exothermic reactions. Well, thermodynamics, when chemists study and scientists study reactions, they look at the big picture, meaning that we look at the reaction as part of a bigger system. And the system includes the reaction and its effect on its surroundings. So the first law of thermodynamics is the law of conservation of energy. And we all know this. We've said it before, the conservation of matter, etc. It says that energy cannot be created, only converted from one form to another. So energy cannot be created or destroyed. It's only converted from one form to another. So the entire energy of the universe is equal to the change in the energy of a system plus the change in energy of its surroundings. So the total amount of energy in the universe never increases or decreases. It just ebbs and flows back and forth. Okay, so the energy of the universe is equal to the system and its surroundings. Okay, so we're going to look at this in our study of thermodynamics. Okay, so just remember, energy cannot be created or destroyed. If one side goes up, the other side goes down. All right, so the first part of thermodynamics that we're going to look at is called Hess's law of summation. And this is the enthalpy change. Oh, enthalpy is an extensive property. So I want to make sure I bring that up. Extensive property. The magnitude of the enthalpy, the value of the enthalpy is dependent on the amount of matter that reacts. Okay, so it is dependent on the amount of matter that reacts. If we double the amount of hydrogen here and oxygen that are used, then it's going to double the amount of energy that's released in this reaction. So Hess's law is used to determine the overall enthalpy change for any reaction when different reactions combine and are manipulated that result in the reaction that we're needing to get the enthalpy change for. For example, carbon plus oxygen yields carbon dioxide. And we happen to know the heat of formation for this is negative 394 kilojoules per mole. Okay, that's a known. We also know that 2 moles of hydrogen gas and a mole of oxygen gas yields 2 moles of water and the delta HF, the heat of formation of this reaction, is negative 572 kilojoules per mole. And again, the combustion of methane with oxygen to carbon dioxide and water, this has the heat of formation, this reaction of negative 891 kilojoules per mole. So all three of these reactions, see this negative value? All three of these reactions are exothermic. Now the reaction that we're wanting to know the delta H for, heat of formation, is carbon combining with hydrogen to form methane, to form this methane right here. This is what we don't know. So Hess's law of summation says that you can take these three known reactions, and if you can manipulate and cancel out to get this final reaction, then it's just the summation of these energies to get the energy of formation of this. Okay, so what we're going to do is we're going to look at these three reactions, and just a couple of tips. For example, when I'm doing this, I line up all of these arrows so that way I can see products and reactants all lined up of these three reactions. Also, what I look for is sometimes, like on this reaction, sometimes they won't have a 2 there. They'll just have a 1, and then they'll have a 1/2 here, and then a 1 here. I mean, it's the same ratios, except here they're using a 1/2. So when I see these like this, what I'll do is I'll go through and I will, if I multiply this reaction by 2, then 2 times 1 is 2. So I'm getting the same thing, right? And then 2 times 1/2 is 1. And then 2 times 1 is 2, right? So I get the same thing. I'm just dealing now with whole numbers instead of fractions. Now, one thing that you have to remember in Hess's law is that if you do something to this reaction, remember this is an extensive property, so it is dependent on the amounts here. If you do something to this reaction, you have to do the exact same thing to the delta H value, okay? So we're going to see this. So what we're looking for here, I've taken this reaction and I put it down here. So what we're looking for is to manipulate these three reactions to get this reaction. So what I do is I start looking for, well, here I see CH4 as a product of this reaction. But if I'm looking at the products of all three of these reactions, I don't see a CH4 over here. So there's no way that I can add these up to get a CH4 if there's no CH4 over here at all. So I do see a CH4 here though. So if I can get this to this side, then I'm on my way to getting this done. So what I do is I can flip this reaction. Okay, so I can write CO2 plus H2O yields CH4 plus 2O2. So what I've done is I've taken this reaction here and I've just written it backwards. I've flipped it. Okay. Now, the one thing you have to remember what I said. If I do this to this reaction, I have to do the same thing to its HF value, its heat of formation value. So since I flipped this reaction, this value also gets flipped. So instead of being a negative 891, now it's going to be a positive 891. So I'm just going to mark out that negative sign there. Okay, now I'm going to look. I have a CH4 here and I have a CH4 here. Where over on this side now I need carbon. Well, I see a carbon here and I need 2H2 and I see a 2H2 here. So what I need to do is I need to now look at what I can cancel. So what I mean there is that if it's a product on this side, it can cancel with a reactant on this side. So say, for example, I have O2 here. I have one O2 here and one O2 here. That's two O2s. I have two O2s. So if I look on this side now, this is a reactant, right? Now we're looking at right and left. That's why I line up my arrows so it's easy to see. This can cancel this. So if I have two O2s on this side, it can cancel with the two O2s on this side. Okay? Now, the same thing with the water. I have two H2Os here. Oops, I forgot to write. See, I have two H2Os. I forgot to write this coefficient there. And I have two H2Os here. So these two H2Os can cancel with these two H2Os. Okay? So now what I have is I only want this CH4 left over. So I haven't crossed out this CO2. So what I'm going to do is come over here and look for a CO2, and I have one here. So I know that these two can cancel out because this on this side cancels this on this side. So all I have left over here on this side now is the CH4. Now, when we cancel right and left, it doesn't do anything to these. The only time it changes these is if you have to flip the equation, okay? Or sometimes we have to multiply the equation by 2. Like if I only had one, if I had two H2Os here, but only one H2O here, then I'm going to have to multiply the entire reaction by 2 to get two H2Os so those can cancel. And if I multiply this reaction by 2, I have to multiply this number by 2. But we didn't have to do that here, so I'm not doing that. I'm just canceling out. When you cancel out, that doesn't affect this number. Okay, so we have CH4 here, and that's the only thing that I have left on the product side that I haven't canceled out, so that's good. So when you get one side to equal out, the other side should equal out. So let's look. So I haven't canceled a carbon here, so that leaves this carbon here. Two H2s here, two H2s here. Okay, so I've canceled everything from these reactions, these three reactions. Okay, I've manipulated and canceled so that it does equal my final reaction right here. Oops, I didn't want to do that. Let me go back. I just wanted to erase. Okay, erase this. So again, I've manipulated and canceled from these reactions that I have known values for to end up with a reaction that I wanted that I don't have a value for. So what I'm going to do now is once I've done this and I've gotten the reaction that I want, then we just sum up these numbers. Okay, that's why it's called Hess's law of summation. These reactions sum up to give me this reaction. So these numbers will sum up to give me the delta H of this reaction. Okay, so this is where we pick up our calculators. All right, so we have a negative 394 plus a negative 572 plus the positive 891. Okay, and that's going to be negative 75 kilojoules per mole. Kilojoules per mole. So this reaction, the formation of methane from carbon and hydrogen, is an exothermic reaction that releases 75 kilojoules per mole. Now what that means per mole is each time this reaction occurs is 1 mole of reaction. So if the reaction happens twice, that's 2 moles of reaction. 3 times, 3 moles of reaction, etc. So each time this reaction happens once, it releases this much energy. Okay, so that's Hess's law of summation. Now, we can also calculate this using the heat of formation. This is just another way to do it. Now, this same concept can be used to calculate the enthalpy, but we're using the formation of compounds. Okay, so we had to have a different, for the heat of formation, a different equation. So the equation is the overall heat of delta H, the overall enthalpy for this reaction is, okay, now this little symbol here means the summation of. You're just going to add up. N is moles, and HF is the heat of formation of a compound. So we're going to add up all the moles of the heat of formation of all of our products minus the summation of the number of moles of heat of formation of the reactants. Now, I know that looks complicated, but what that means is we're going to take the heats of formation for all of our products times the number of moles it is minus the heat of formation of the reactants. So what I like to do is when I'm doing the enthalpy change for this, I'm going to do products minus reactants, just like this. Okay. And then I'm just going to start summing up. So I'm going to look at my products. Well, here I have CH4 and I only have 1 mole. So I'm going to go to my table, and these tables are going to be supplied for you. And I'm going to look CH4 up. Now, a lot of times it does matter whether this is a gas or a liquid. So look for these different states of matter. Okay. And CH4, let's see, where is CH4? Right here, CH4. Okay. So the heat of formation for CH4 is negative 74.9. Okay, and this is kilojoules per mole. These are given in kilojoules per mole. So that's kilojoules per mole. All right, let me underline these. So how many moles of this do we have? 1. Okay, so I would, put my number here. Since it's 1, it really doesn't matter. Okay, now that's all I have for my products. Now I'm going to list out my reactants. Well, one thing that I want to say is that the heat of formation of all elements, of all things that are in their elemental form, is 0. Okay, just like when we're talking about redox and the oxidation numbers. If it's an element that's just sitting by itself, the oxidation number is 0. Same thing with this. The heat of formation of individual elements is always 0. So here on the reactant side, this is an element, so that's 0. This is an element, hydrogen gas, diatomic element, that's 0. Okay, so here's what we have. Negative 74.9 kilojoules per mole minus 0 is negative 74 kilojoules per mole. Now, if we look back, okay, and Hess's law of formation told us that it's a negative 75 kilojoules per mole. Okay, so 74.9 rounds off to 75. So we get the same answer using 2 different methods. Okay, Hess's law, where you're summing up individual reactions, it's a little more involved. And then the heats of formation, where you take the products minus the reactants. So it's the summing of all of the moles of the products minus the summation of all of the moles of the reactants, and it gives you your overall delta H. All right, so let's look at a little more detailed example. So let's take this for example. Now this is CH4 plus O2. This is a combustion of methane. And let me erase this. If we look at that, this is that reaction right there. Okay, so it's this same reaction. We should get a negative 891 kilojoules per mole. So right here, negative 891 kilojoules per mole. Now we already know what this is. We're just going to use the heat of formation method to verify this. Okay, all right. So what I do is, all right, products minus reactants. And this is just my method. You don't have to do it this way. That just keeps it straight for me. All right, so here are my products and here are my reactants. I'm going to do my products first. So H2O. Okay, so I'm going to come over here and let's say this is liquid H2O. So H2O liquid right here, negative 285.8. Okay. Now I'm going to multiply that by the number of moles, so that's going to be 2. Okay, now carbon dioxide. So I'm going to come over here and find carbon dioxide right here. Carbon dioxide is a negative 393.5. Let me fix that. Negative 393.5, okay, times the number of moles of carbon dioxide is 1. Okay, now let's do our reactants. Okay, we have 2O2 here. Well, remember, this is an element, diatomic oxygen, so it's 0. Okay, so we get a 0 there. So I can just put 0 just as a placeholder for that reactant. Now CH4, let's see here, CH4 right here, negative 74.9. Looks like a 1. Negative 74.9 times the number of moles, 1, we have there. So what I do is I draw a line here now, and I add all this up and get a number, add all this up and get a number, and then I have my equation there. So this is going to be negative 74.9. I already know that. Okay, so let's get this. Okay, so 2 times negative 285.8 is going to be negative 571.6. Okay, this is going to be negative 393.5 since it's by 1. Now add these up. So negative 571.6 plus negative 393.5. Okay, that's going to give me negative 965.1. Okay, so this minus this is equal to, it should be the delta H of our reaction. Okay, now this is the number I'm expecting to get. Remember, because we already know this. So this is the number that I'm expecting to get. Okay, so negative 965.1 minus negative 74.9 is equal to negative 890.2 kilojoules per mole. Okay, so let's look. Negative 891. Okay, so this is only what, a 0.8 difference. Okay, 0.8 difference. That's nothing. So what you're going to see is you're going to get these numbers that you calculate are going to be slightly different. That's because this right here is a more accurate way than Hess's law of summation. So it's going to give you a little more accurate number than Hess's law. Okay, the more accurate you get, okay, the numbers are going to be a little bit different, the more accurate method. Okay, so this is the heat of formation using to get the overall enthalpy, the heat of formation of individual compounds. Okay, now there's one more method I want to show you about, and this is called bond energies. Okay, and the heat of formation can be calculated by looking at the bonds that are broken and formed. So this is a little more detailed than the heat of formation and more detailed than Hess's law of summation, where we're looking at the enthalpies of entire reactions. Okay, now this is going to be the summation of the number of moles of the bond energy, Be is bond energy of bonds broken minus the summation of all the moles of the bond energies of the bonds formed. Okay, so just like in the heat of formation, I remember broken minus formed. Broken minus formed. Okay, let me write it up here. Broken minus formed. Okay, because I need this area right here. So what we're looking at now is individual bonds that are broken compared to the bonds that are formed. Okay, so one thing when you need to know when you're doing this is you need to know how to draw the Lewis structures for these compounds. Okay, so remember Lewis structures, that's nozzle. So because you need to know that this carbon here is bonded to 4 hydrogens, and this is the Lewis structure for that. And I get that by doing nozzle. I also know it from experience. So that way I can see that this carbon is bonded to this hydrogen with a single bond. Okay. And so I can look over here and look at the bond energy. How much energy is in that bond? Well, right here is a carbon hydrogen single bond, and that's 413. Okay, 413 kilojoules of energy. All right. And so I have this bond here that needs to be broken, this bond that needs to be broken, and this bond that needs to be broken. So that's in CH4. Now, we also have O2 here. So if I were to do the nozzle Lewis structure for O2, I'm going to see that O2 is a double bond like this. Okay. I need to know that's a double bond because I look down here and see O2. Well, it just gives us O2 there. So that's 498. So to break that bond here, it's 498 kilojoules of energy. And then these are the bonds it's formed. Okay, so I need to know what the Lewis structure is for CO2. Well, that's this. Okay. So I need to know how to draw that because here I see that this is carbon double bond oxygen. Now these are single bonds up in the top here, multiple bonds down here. So one thing that I want to point out is that this C double bond oxygen that you see here, it says that it's 745 unless it's in carbon dioxide. So if it's in carbon dioxide, then it's going to be 799 instead of 745. So when do we see a carbon double bond oxygen that's not in carbon dioxide? That would be something like if we had CH2O, okay, and it looks like this. So, okay, this is formaldehyde. So here we have a C double bond oxygen, but it's not in carbon dioxide. So that would be your 745, okay? So I just want to make sure I point that out. Okay, and then we have this H2O. Well, we know that H2O, we draw it out, looks like this. So we have 2 single bonds of oxygen hydrogen. Okay, so I need to look at all of these and I need to do broken minus formed. Now remember, it's moles of broken minus moles of formed. Okay, so here I have 1, 2, 3, 4 moles of the carbon hydrogen bonds. So I need to look over here. Carbon hydrogen is 413. So 413. Okay, what else is going to be broken? It's going to be this O2 right here. So we have 2 moles of the 498. Okay, so that's the bonds that are being broken. Now the bonds that are being formed, I have carbon dioxide here. So I have 1, 2 carbon oxygen bonds in carbon dioxide. So that's 799. Okay. And then here I've got 2 hydrogen oxygen bonds, right? 2 of these, but there's 2 moles of it. So that's 4 total oxygen hydrogen bonds. And let's find that right here. Oxygen hydrogen bonds, that's 467. Okay, so now I need to add these up. Okay, so it's the summation of these, and it's broken minus formed. Okay, so let's see. So 4 times 413 plus open parentheses, 2 times 498, close parentheses. That gives 2648. Okay. Now the other side, open parentheses, 2 times 799, close parentheses, plus open parentheses, 4 times 467. That's going to give us 3466. Okay. So it's 2648 minus 3466. That's going to give us negative, let me write it right up here, negative 818 kilojoules per mole. All right. So here we see in our first example, 891, and that's with Hess's law of summation. Okay. And then we saw in our last example, when we were using the heat of formation, right, we got 889.6. And here with bond energies, we got 818. So these numbers are slightly different, but right down here at the bottom, while these values are not the same, they are all exothermic, okay? And they're all within 2% of each other. So that's okay, that's an acceptable margin because we're getting more and more accurate. Now we're looking here at bond energies, the energies on these bonds. Okay, so for reactions occurring in the gaseous state, see, this wasn't all gaseous, but for all reactions occurring in the gaseous state, the bond energies give a very, very close approximation to the enthalpy changes calculated with standard values for equations. Okay, so those are the 3 different methods that we're going to use to calculate the delta H, or the change in heat energy in these reactions. Okay. So one more thing I want to talk to you about. These 2 molecules, or these 2 reactions, are on your homework. And it's asking you to do the bond energies, the bonds broken minus the bonds formed. Well, here's where I'm going to write this down. The honk rule comes in. So these are much, much more complicated than the molecules that we're doing nozzle with, right? In nozzle, we're usually just using 3 or 4 elements. But here we've got lots and lots bonded together. And knowing how to draw these out just comes from a little bit of experience on drawing molecules alive. So what you'll see here is, see this carbon and this carbon and this carbon? Organic molecules form what's called a carbon chain, like this. So this has a 3-carbon chain, and then things are attached to this carbon backbone. So if we'll look at just this section right here, CH2, this is the 2nd carbon, right? Well, if this carbon is bonded to this carbon, that takes 2 of the spots that carbon can bond. Remember, carbon usually makes 4 bonds. So there's only 2 more spots for something to bond. Well, H2, it tells you what's bonding to that. H2, like this. Okay. Now, on this carbon right here, we see H2 plus OH. Well, H2, right, we can do this. So that's 2 spots for carbon. So on this other spot for carbon right here, we have an OH bonded to it. And this is called, in organic chemistry, an OH is called a hydroxyl group. So if we even expand that out even more, we see OH, instead of running it together, we see an oxygen and then bonded with a hydrogen. Now, so remember, for the honk rule, okay, hydrogen can get 1 bond, so there you go. Oxygen usually forms 2 bonds. Here's one, here's one. So what they don't show you here are the lone electrons. So this oxygen is going to have 2 lone electrons on it. Okay, now coming down to this end, we see carbon here is bonded to nitrogen. Okay, so since carbon has to have 4 bonds, or usually has 4 bonds, we see 4 bonds here. Nitrogen forms 3, so this nitrogen forms 3 bonds, so we're going to see the carbon triple bond nitrogen on this end. So that's what you're going to see there. Okay, and this, look, from one problem, this is one problem, this is another problem. This right here is exactly the same as this. Now on this problem, they expand it out like I did, but on this problem, they run it all together. So if you count, there's 3 carbons there, okay? And then the nitrogen, right? CH2 right here, CH2, and then this HO, CH2, CH2, and then the HO. So it's the same. Okay, so I wanted to point that out to you because you're going to have to be counting bonds. So you're going to have to expand this out like this and count all of these bonds that are broken and formed. Okay, and then on this one right here, this right here, it tells you it's this. So that doesn't mean that, you know, that it's separate. That just means that the HCN is an H single bond, C triple bond N. So that expands it out for you. So don't let that confuse you. Okay, so here on this one where we have CH2, and then there's a bond there, CH2, and then oxygen. What that really means is that we have our carbon-carbon, okay, and then an oxygen here. And this is rare. This usually doesn't happen. Remember, back when we were doing the Vesper shapes, you know, I told you if it was 3 bonds, it wouldn't make a triangle, where here it's showing you it is a triangle. Not that that never happens. I just didn't want you to do it back then. But this is showing us that it does happen. Well, here, H2, these H2s, it doesn't show you here, but they're bonded. One's coming towards you and one's going away from you, these bonds for hydrogen. Okay, and this one has the same thing. Okay, so it's this carbon with 2 hydrogens sticking out of it, bonded to this carbon with 2 hydrogens sticking out of it. And then it's bonded here to the oxygen. So that's how this one is going to be expanded out. So when you're counting bonds that are broken, remember, count this CH bond, this CH bond, and then there's 2 more here, this CH bond, this CH bond, right? Now we have a carbon oxygen here and a carbon oxygen here. Okay, so make sure you count all of these bonds that are being broken. Oh, and there's a carbon-carbon here. All of these bonds, you count how many of them there are that are broken, because remember, it's broken minus formed. Okay, so just a little help on those last 2 problems that you're going to be working out on your homework. All right, so that's it. Make sure you slap that like button right across the face. Give me a thumbs up, subscribe, and leave me a comment.